You can speak now. Don't be shy. It seemed like it was too long. Is that a fair?
It was just a wide list. I kind of in the. I think they were just like, I mean, the problems themselves are normally kind of long. I think that's what was it.
Okay.
So like the wide list was just a lot, make sure you see writing and stuff.
Yeah.
I think if you only like. If you want
Say that again.
4 of them were part A, B, and C. So that was a bit, I think that kind of added some length.
So 3-parters.
Yeah, it added some length to it, but it wasn't like.
Didn't you do it? Yeah. All right.
Yeah, it's one. All right, well, I've given out all the tests that I have in my possession. Well, to the people that are here. Shall we go over it?
Yeah,
Yeah, I'd like to.
Pardon?
I would like to.
Okay. Problem number 1. So I have 2 subs or substations, in the vernacular of the power world. We have 2 substations, which is another way to say a bus. Substation bus is the same thing. So I have one end of my one substation, 73034.
you're not sharing your screen, Paul.
Oh. Thank you. Can you see it now?
Yes,
So 73034 at an angle of 30 is one end. Then you have an impedance in between of 100 at an angle of 60. And then the other bus or other substation voltage is 66, 395. And its angle is at an angle of 20. So this one was essentially find S, P, and Q for this particular problem. Does this look familiar to a problem you may have seen in the past? Maybe on homework number 1? It's pretty much the same thing. And if you remember when we talked about in class, and you can go back to the videos, but what I said is the voltage drop across here is how you can determine the current. You know, or you have the ability to calculate the voltage drop. So V drop is equal to V bus 1 minus V bus 2. That's your voltage drop. And then to solve for I, it's your voltage drop divided by 100 at an angle of 60. That's just V drop and I. But what my question was, what is the total power per phase that is being transmitted from bus 1 to bus 2? It's not the power that is dropped in the line. It is the power that's transmitted across the system or from bus 1. So wouldn't S equal V bus 1 times I conjugate? Almost everybody put the voltage drop across there. I didn't say, what does the line consume? Okay. And a lot of people did this. This is a big no-no that we talked about this at the beginning of the semester. We said that P equals V squared over R, or Q equals V squared over X, or P equals I squared R, or this equals V squared X, right? We never once said S equals V squared over Z, did we? Because if you recall, this number here, V, it is a magnitude only. This has to be the magnitude of the voltage. It is not the magnitude in the angle, because if you square it, you're going to end up with a P that has a real part and an imaginary part, if you include the angle. And a lot of people put on the test, the power equals 3,552 plus J, 7,638 watts. How can you have a J term and it be real power? S could be that, but not P. And the way that we got these equations here, these over here, so P, we know, is V times I in an inductor. I mean, in a resistor. So this is equal to V divided by R. But remember, the actual equation is S equals VI conjugate. So if it's purely a resistor, this here, this, well, you want to go ahead and take and then multiply this by the cosine of theta. So this has to have the conjugate term. Once you multiply by the cosine of theta, you're basically multiplying by the resistor. So because it is the cosine, V times V conjugate divided by R, because the conjugate of a real number, it doesn't change. So this has an angle, V at an angle of theta, times V at an angle of minus theta over R. Isn't it by default? Have to equal that. Can't have angles in there and make this work. Okay. And because of that same concept, you got to be very careful about doing the V, because once you do the conjugate, all bets are off and you start to lose the P and the Q parts of it, okay? So I'm not going to give you the specific answers, but I'll give you enough that I feel is enough to, if you want to solve this problem out, you're welcome to do that. I'm not understanding. You can draw a power triangle here, can't you? Pardon? Show you what? Do you need me to show you the power triangle? As to why what? I'm just giving you one way. You could have done it the power triangle way. Either one works. The power triangle one is S equals VI conjugate, right? That's going to equal P plus JQ. Same thing, isn't it? The reason why I didn't show you the power triangle is a lot of people tried to get P and Q by using V squared over Z or something like that. That's why I wanted to emphasize that. I didn't put the power triangle one because I thought that one would have been just, it would have revealed the answers, but I was trying to specifically show you why the V squared over R and the V squared over X work out the way they do. Okay, but either one would have worked. Right? Other questions on that? Very quiet. Are we still confused or? Do we need more time to go over this? All right, well, interrupt me if we do. Number 2, draw a picture. We have a 200 volt source and 200 volt RMS means this is at an angle of 0. Some people are trying to convert the RMS to a peak value. You don't do that. This is problem number 2, right? Oh, okay. I was just like, let me do part A and then we can get to that, okay? So this is 200 at an angle of 0. That was the RMS value. So that's what you write in as your phasor number. Your voltage is 200 at an angle of 0. Then you put 100 here. Then we can put in a box. This is 100 plus J20. Now there's a bunch of different ways to solve for this. The question was, find the total real and reactive power and power factor. So you could have solved for the current here and the current here because those voltages are in parallel. Then you sum that current, I total, and then you do S equals VI conjugate. That's perfectly fine. You could have also done the parallel combination, which some of you did. And this is 100 in parallel with 100 plus J20. I encourage some of you folks to be very careful and go back through your work, because a lot of different ways to get 100 in parallel with 100 plus J20 is what you all thought, but there's only one way, right? It's product over the sum. But then this would have given you the same result for I, and then you would use the same S equals VI conjugate. Okay. Once you do that, draw the power triangle. And then the third step is find the capacitance of the capacitor, or find the capacitor that's connected across of the load. So I was really looking for a farad value, but if you gave me an X sub C, that was fine. Well, when I did my power triangle here, it kind of looked like this. This angle here was pretty low. Let's just say it's 4. Okay. The cosine of 4 equals what? Let's just say it's equal to 4. I don't know what it is exactly, but I know it's greater than 0.8. So you didn't need to put a capacitor there. It was already better than 0.8 lagging. A lot of you people tried to still put a capacitor in there to get it to 0.8. But then it was no longer lagging, it was leading. And that's just as bad as doing a lagging power factor, because again, that's going to increase the magnitude of the current, and the utility is going to have a charge for that. So what you all were doing is you were getting a power factor, it was 0.9, then you're saying go to 0.8. What you were actually doing was putting it to go negative in this direction. So what you ended up doing was coming up with a power triangle that this was the cosine inverse of 0.8. You added too much capacitance, and now you made it leading. If you got the right numbers. Some people had different incorrect numbers. And if you had incorrect numbers, I tried to give you credit based on, the approach that was taken. Yes, sir.
So since it's kind of better power factor, are you saying the trick question, or is there one the right answer you want to communicate?
The right answer was 0. X sub C or C equals 0. It already exceeds 0.8. Don't add a capacitor. I don't think was that a trick question?
That definitely tripped me up a lot, because I mean, that made me redo my calculations for the earlier part like 3 times, because I kept getting a really small answer. And I was like, that can't be right. I don't know why he would intentionally like ask us to do an extra step that would make it worse. Because like I said, I was getting
I didn't
like,
ask you to make it worse. I added to go to 0.8 lagging.
which
0.8 lagging. It was already better than 0.8 lagging. So
yeah.
you have to improve it.
So that you mean like that's kind of strange wording to ask us to improve it to a point where it's actually making it worse. So I mean, I kind of did the exact same thing. I did the negative angle because that was the only thing that made any sense to me.
But that would not be a lagging power factor, right? It would be a leading power factor.
Exactly, which is why I was really confused, and I just put down something to have anything there, because I would consider that kind of a trick question, I guess.
Okay. It wasn't meant to be a trick. It was just to say you're already better than 0.8, so you don't have to do anything. There's nothing you need to do.
Maybe could have said at the end if it needed it or something.
I've done that in previous times, and then people all of a sudden get really confused when you do that. Once you give options like that, now you get the other end. So really what I'm trying to do is assess, do you understand drawing the power triangle and putting the power factor correction on there? What are you ultimately trying to do? If you had drawn this little triangle and show this, and I still give people a boatload of credit if they did improve it to 0.8 leading, right? So it's not like I gave folks 0, but to get full credit, you just said there's no capacitor necessary. Okay. Any other discussion on that?
Hey, Paul.
Yes,
So I know you scaled the score, but is there any way that we
I actually
can
didn't scale the score.
Oh, okay.
Where do you think it is? It's on Brightspace. Should be in your, it should be in your stuff. Doesn't show you on your test. Okay. Maybe you should look first before you ask the question. It should be in there. It's on the, it should be on your test on the third page. So that way you have privacy, but it's already in Brightspace too.
So what's the perfect score supposed to be for this?
To get
test?
100,
Was
to
it
get
just
all the
100 is the
points.
perfect score?
pardon?
Is 100 is the perfect score for this
To
test?
get a perfect score, you had to get, I think it was 130 points. Is that
Yep.
your question?
Yep.
All right, number 3. So there was a little bit of confusion on here, and we talked about this in lab and we talked about this during class. You're not going to connect a transformer to generator 1, whose transformer winding for T1, generator 1 is not going to connect to the 200 kV winding, correct? So if it was confusing, I just wrote this down to say, these are the values. Go ahead and put the right turns ratios. Here's G1, G2, T1, T2. So this, you should have known, was configured this way. And this one, this transformer, was configured that way. It steps it up to the transmission line voltage level to reduce line losses, and then steps it down. Because some of you all said, you know, these were reversed. This was going from 200 kV on the generator winding and stepping it down to 20 kV. So your V-base values were a little off. Okay, you have to be able to interpolate the data just like you did on the per unit one line diagram, where we just had a rating of the transformer that we would step it up or down. We would just say, here's a low voltage winding, here's a high voltage winding. You had to figure out which side was the low voltage connection and which one was the high voltage. The only one that we did on this one is to convert it to per unit. I didn't say do Y bus, I said do per unit. So the only one that, well, there's 2 parts. So you had an X line equal to 120. So you had to divide that by Z base to convert to per unit. And then my load, as we did in lab, all you took is your S and divided by S base. Some people tried to force it to have ohms, which would make it a constant impedance load, which is okay. But why not just divide it by S base? That's sufficient for the lab. It was sufficient here.
You're talking about the S. That
The load on connected to bus 1.
So the 48. Okay.
Yep.
Right. That's what tripped me up. I just didn't know what to do with that load on there. I was like, oh, I don't remember.
Just like we did in the lab.
Right.
The other thing I will say too is some people were trying to force S load to have an S base. It doesn't have an S base. It is the actual load that is connected to that bus. So you can't say that it has an 80 MVA base because that doesn't apply. With transformers, we only have one S base. The load isn't purchased at an 80 MVA base because then it would have been given to you in per unit. So what impression that gives me, there's still a little bit of a miscommunication or misunderstanding of how to do per unit calculations. Yes, sir. The 48 megawatts plus 64 megavar. Well, the S is in the positive direction. So when you go S equals VI conjugate, you got to take the negative of the angle. So that would be a lagging power factor. Okay. But you would still draw it as, 48 or 0.48 divided by plus J 0.64. You still have a positive. It's only that the current lags. Okay. The other thing too is some people were putting units of ohms on their per unit diagrams. That's a big no-no. The whole purpose of doing per unit is to get rid of all the units, correct? Remember the gas tank example? Your gas tank is a quarter full. It doesn't have 7 gallons or whatever your size tank is. It's a quarter. It's not a quarter gallon. It's a quarter. It's the same thing here when we do per unit. Any questions on that? All right, let's go to number 4. There are a lot of challenges with this one. I'm just gonna draw this as Z. I'll put Z line over here. And this voltage here, we'll just call the magnitude was 208. So it's a balanced system and all the voltage magnitudes are 208. So what I asked for was to solve for the line current here. Correct? The problem is some people just said, oh, okay, well, it has to be 208 divided by Z line. That's not right, because the only way that it would be that case if these lines were shorted out at the end. And even then, that wouldn't be right. So the way to solve this problem, we talked about this in this class, is to convert this to a Y. And because this is converted to a Y, now what I need to know is I can go ahead and convert this. This is across 2 lines. Now I have to convert this to, I'm going to convert both sides to Y. So this is my Y circuit. I have a Z line. I have my Z at my load. And this is my neutral connection. This is 120. Or let me write it out. It's 208 divided by the square root of 3. This voltage here in balanced systems is 0. This voltage is 0. So all I had was a series circuit. I had 120 at an angle of 0. Then I went to my line impedance. And I went to my load. Calculate that current. And in the line, there's only one line current. That's the same exact current. So you just had to do a delta Y conversion. And remember, ZY times 3 equals Z delta when they're all balanced.
This is probably the trickiest question for me.
I
Where
can't
are you
hear you, I'm
getting that?
sorry.
I was saying this is probably the trickiest question for me, but where are you getting that 208 value from?
It's on the, if you look, it says V line equals 207.85. You see it between terminals A and B.
Okay, yeah, I got that. You just rounded it up.
You take the 207.85, divide by the square root of 3 to convert that to a phase voltage,
Okay,
and you get your value.
okay.
Yes, sir? Correct. Do a delta Y conversion. And the reason why you did that again is because this voltage here is at 0 volts. Then you could say this voltage here is at 0 volts, and you can draw that common connection because they're electrically at the same point. Now it's just a simple series circuit.
Do you do anything with 1 plus J?
This is the Z line, right?
Oh, I thought we were talking about.
That's the load. You have a line and a load. So you have to drop both of them. Pardon?
I think I had those split.
Okay. Once you have that, then you should be able to solve, because now you know I and V. So S equals V phase, I phase conjugate. Don't forget I need a 3 because it's a 3-phase system. That'll give you part B. And then part C is, all I needed was the magnitude of the line-to-line voltage at the terminal. I should be able to calculate the voltage drop here. Once I have this voltage drop, we'll call it VZ. Square root of 3 times VZ equals my V line-to-line voltage. Okay. Questions on number 4? So I think Audrey said this was the most challenging problem. Is that what everybody agrees with, or 6 was more challenging?
I
think
thought this
six-
one was pretty challenging.
I think 6 part B probably was in some ways the hardest problem,
Yeah.
at least to figure it out. But That's just, it's, beauty's in the eye of the beholder, whatever you think was the more challenging one. Oops, somebody's gonna chat. Thanks, Adam. Is it really that challenging though, when you do that conversion?
I didn't know it would be converted.
Yeah, once I saw, like, once what we talked about after, I was like, oh, I should have thought of it that way. I didn't think of putting it like that.
Yeah, the nice thing is, once you have that delta converted to a Y, you get that 0 voltage reference point, and then you have another 0 voltage reference points. It really simplifies the circuit sound a lot. There are other ways to do this problem, but it's much easier to do it this way. I mean, you have to do a lot of stuff with square root of threes and adding and subtracting things. This way we do single phase equivalence, right? That's what we're always trying to do in this class. Figure out what the single phase equivalent is and do our calculations, and then we get the results. Number 5, I'm not going to draw it all out. Number 5 was just building a Y bus. And let's look at bus number 1. I tried to make it easy. You had a current source. You had J.25, and then you had a cap. This is minus J4, and then you had all the other impedances. An inductor, when you model it as an impedance, does it have a positive J or a negative J when its units are ohms? An inductor. Yeah. So these were all in ohms or per unit of ohms, correct? Because J.25 has definitely not been inverted. So all you had to do was invert all those. And some people tried to put them in parallel and all that stuff. You didn't need to do that. That's the beauty of Y bus. They're all just connected to a bus. As long as they're not in series, you literally just start adding up. Y11 is equal to 1 over J.25 plus 1 over J minus 4 plus on and on and on and on and on. The one thing that I would say is when people were inverting, they were forgetting about the J terms, because when they were building their Y bus, their diagonals were positive. I mean, the diagonals were, yeah, they were the off diagonals were negative and the diagonals were positive. And usually when you have more of an inductive circuit, that tends to be the case. And so for whatever reason, you weren't inverting the J term and getting that value, because that J.25 inductor in ohms looks like minus J4 ohms for impedance, okay, or for admittance. So after that, it was just literally, we talked about it in the lab, just go ahead and rinse and repeat, do the same thing over and over and over and over and over.
Can you say again, like, how to know which ones are negative and positive?
Sure. So usually all these are going to have positive real parts or negative real parts, sorry. And all the off diagonals are going to be positive. And that's because most transmission lines, they look primarily inductive. Some are capacitive, but they're primarily inductive. So if I do 1 over J, that's minus J. So if I put it here in the self-admittance, it just adds together. But the Y12 is taking the negative of the admittance between bus 1 and bus 2. So that's why it becomes a positive number. Matt first and then Connor. All right, want to see me after class then? Connor?
So from left to right, that negatives could all be negative. Those numbers could all be negative.
The diagonals, you mean?
Yeah.
Yes.
So,
Those usually will be, not always, but they usually will.
right, so the off diagonal numbers,
Are generally positive.
right, and I had them all negative at first. Would they still be the same number? And I could switch the sign?
Maybe. It depends on your work. I have to
That's
see.
what I did, so I was like, I don't know if these are supposed to all be positive, so I don't know what I did wrong, so I just changed them all positive.
Because you might not have done the J terms. And then you got to be
Right.
careful because you had so many, like a capacitor is minus J4 is only positive J.25. So when you add things, you got to be careful about adding and making sure you have the J terms correct. Any other questions on number 5? There was a 4x4 matrix that you had 4 buses.
Right.
So what would you do? Lower the what's this in Y bus? I had no idea what.
What is Y bus? Y bus is an admittance matrix. How would you add power, which has the units of watts or VARs, into something that has the units of Siemens or Mohs?
That's what I thought. Saw it in there.
Yeah, more often than not, when you model in the real world, remember, we talked about Y bus is just a model of the system. Load is not the system, that's the customers paying the bills. So our system is modeled as an admittance matrix, doesn't have anything to do with power. Okay, doesn't even have voltage or current, right? We talked about those current injections, we always would put those on the outside. If you want to make it a constant impedance, you can add those in there, but very rarely is that done unless you have, maybe it's a 40 megavar cap bank. And that's going to be switched on, but that's a fixed impedance. So as the voltage goes up and down, it's going to put more or less reactive power on the grid. Okay. But the most of the time, remember, the customers are paying the money for the load. If the load drops below what they expect or what they want, then you're not getting compensated. So you do what you can to make sure that the customer load is maximum, because you're not going to get paid as much. You've already paid for the infrastructure. You might as well use it to its full capacity. Okay.
I have a question, Paul.
Yes.
What would you do with the S3 and the S4?
I thought that we were just talking about that. Did that
Oh, I
make
guess
sense?
maybe I didn't hear it. Sorry.
Yeah. So what are the units of S3 and S4?
MVA.
Yeah. What are the units associated with the admittance matrix? It's Mohs, right? It's 1/ohms or Mohs. So how can you add something that has the units of MVA into something that should only have the units of Mohs? So you would treat this as an external, you're doing calculations to try to figure out what the voltage and currents need to be in the system, and it's based on these load values. Okay. Does that answer your question, Ben?
Yeah, I think so.
Okay. Number 6, I'm not going to do A because we're probably beating a dead horse, but that's just open and short circuit tests. Y'all should be pretty comfortable about doing those. This is single phase. You don't need to do any square root of 3s. So just treat that as single phase. Part B was, now all my circuit looks like is this. Okay. And I said, if it's delivering 0.8 lagging power factor on the low voltage side, the question is, what is the efficiency? Well, 0.8 lagging power factor means it has 40 kilowatts, right? Is what it's supposed to be doing. And if you look at the short circuit test, the short circuit test says this consumes 615 watts under full load conditions. The only thing that causes losses is the current through it, I squared R. This test, the full load or the short circuit test, is done under full load conditions, full current going in there. So P out is 40K plus 615. P in, sorry, not P out. And P out is equal to 40. That's it. You had to multiply 50 kVA by 0.8, add a couple numbers together, and then divide for efficiency. Remember, efficiency is P out over P in. It is not S out over S in or V out over V in. It's only P. Questions on that? I thought this one would be the hardest one to understand, but it probably is the overall easiest problem to do, right?
I just forgot the basic equation for efficiency. I was like,
Yeah.
I haven't done that like since last semester. so-
You forgot output over input?
Yes.
Okay. You could have asked me, I would have given it to you.
Yeah, I was remember.
Or I'd have looked at you saying, really?
Yeah.
Then I would have given it to you.
Well, I'm thinking about so much more complex equations that the easiest ones just slip right by.
I remember studying this and like, I didn't even.
Paul,
Looked over to get efficiency and I'm like, We don't need that.
Yeah, it's just P out over PM. We do that a lot in real world because we want to see how efficient our system is, how much, and it's becoming more and more important because we have EV charging. The efficiency of the grid has to be included in the calculations of are EVs the end all be all for cleaning up greenhouse gas emissions. They're not perfect. They have a lot more line losses on your system, and those line losses have to be coming from the fact that you're putting more power on the grid. So line losses are going to increase. So not perfect. Yes, sir.
Was the 40K given the problem?
The problem description says it's a 50 kVA, blah, blah, blah transformer. Remember, power factor is the definition is P over S. So P is equal to S times your power factor. It says operated at full load. This is 50 kVA. This is 0.8. And for this last one, all I wanted to know was the phasor diagram. So you pick your voltage as your reference, and then your current is here. Calculate what the current is on the low voltage winding. And this here is the inverse cosine of 0.8. That's it. That was a test. Any last minute thoughts? All right, so everybody look at their grade. Now you have to take a ratio of that to 1/30 to get your real grade. I'm kidding. If you get 130 points, your grade is 130 out of 100. So your grade is actually going to be a function of whatever your score is. That's your script, your actual raw score. Don't take whatever you got and divide it by 130. Divide that by 100. Or do you want me to divide it by 130? It's fine with me. Okay. I do that for two reasons. First off, a lot of you aren't used to taking my tests, and usually you complain, comment that my tests are hard. But I don't like to give people points because in life, most people don't give you things. I like people to earn their points. So you earned every point on that test. Different philosophy, right? You say it's a scale. I say you earn those points. Unless you want me to divide it out of 130. Okay, and then one other thing too, because the test went so long, normally I like to race right through. I was supposed to cover new material today. I will let you go early. Unless you have further comments. Or do you want to start more material?
I'm good.
TV land?
I'm okay, thank you.
Yeah, I'm good.
Thanks for the review.
Yeah.
You're welcome. All right. If I don't have anything else, have a great day, everyone.
Hey, Paul.
Oh, does somebody have a question?
Yeah, it's just me, Adam.
Go ahead.
We can wait till after the recording is done. It's just a question